Assalamu alaikum students. The topic of today's video is the relationship between CP and CV. So I'm going to explain the relationship between CP and CV, and I'm going to explain how CP minus CV is equal to general gas constant R. So first of all, you need to know that I'm going to explain how CP minus CV is equal to R. Okay. So, first of all, moving on towards the heat capacity at constant volume, the heat capacity at constant volume CV is given by change in energy divided by change in temperature at constant volume. I have derived this relationship in my previous video. If you do not know about this relationship, you can just watch my previous video. And again, I have the value for Cp, and that gives me change in enthalpy divided by change in temperature at constant pressure. So that's the value for Cp. So now I'm going to take the difference between Cp minus Cv. So that will give me Cp minus Cv is equal to, the value of Cp is change in enthalpy divided by change in temperature at constant pressure, and then I have to subtract change in energy divided by change in temperature at constant volume. Okay, so that's the difference. And now, as you know, the value for enthalpy is H is equal to E plus PV. Okay, so that's the value for enthalpy. And now, differentiating this equation with respect to temperature at constant pressure, we can obtain just like this: change in enthalpy divided by change in temperature, again change in energy divided by change in temperature, plus, since we are taking P to be constant, so P will go out, and again we will have change in volume divided by change in temperature. And as you know that we are all doing this at constant pressure, so I'm going to just put a bracket and P here. Again a bracket and P. Bracket and P, because this P is representing that we are performing the calculations at the constant pressure. Okay, so now we have the value for delta H divided by delta T, and now I'm going to plug in this value here. Okay, so again I'm going to write Cp minus Cv is equal to, and in place of this I'm going to just plug in this value. Okay, plugging in this value will give me change in energy divided by change in temperature at constant pressure, plus P, change in volume divided by change in temperature at constant pressure. Okay, so what I've just done, I've just plugged in the value of this, and now I'm going to write minus and this part here, that is change in energy divided by change in temperature at constant volume. Okay, so now what I'm going to do next is I'm going to derive a relationship of del E divided by del T, and then I'm going to plug in that relationship into this equation. So for that, first of all, you know that E here, okay, the E energy is a function of two of the variables. And what are these variables? You know that energy is the function of any two variables. And what are these variables? These are pressure, volume, temperature. So what does it mean? It means that energy is the function of any two of these variables. Mean if we take one of these variables to be constant, then the energy will be dependent upon the other two variables. So since we are talking about pressure, we are talking about the constant pressure here, so I'm going to take pressure to be constant, so my energy will be dependent upon, the energy will be the function of volume and temperature. So as you know that here we have taken the energy to be the function of volume and temperature, so the exact differential of the energy will be, because as you know that energy is a state function, so now I'm going to take the exact differential of the energy, and the exact differential of the energy will give me dE is equal to d change in delta E divided by delta V at constant temperature dV, and again delta E divided by delta T at constant volume. Okay, and that will give me dt. Okay, so how I have just derived this relation in the case that I have just told you before, that energy can be described by any of the two variables from PVT. We can describe energy as a function of pressure and volume. We can describe energy as a function of volume and temperature. We can describe energy as a function of pressure and temperature. Since here we are describing the energy as a function of volume and temperature only, so in that case my delta E will be equal to the change in energy with respect to volume when we have taken temperature to be constant, and then change in energy with respect to temperature when we have taken volume to be constant. Okay, so that is the value for delta E that we are deriving. So now I am going to divide both sides of this equation by dt, that is delta T at constant pressure. Okay, so now I have just divided delta T here and delta T here, and that will give me, you might have noticed that what I have done here is that I have changed the signs of differential, because here this was a differential that was completely independent, and now this differential here is dependent upon the temperature, and I'm saying that this energy is now being dependent on the temperature, and now when this quantity is being dependent on temperature, this differential will be changed into partial differential, and when it was free, when it was alone, this differential was d, but now when it is now dependent on temperature, I am going to change this d into the partial differential sign, because now this energy is being differentiated with respect to temperature. Okay, so now since we are taking this to be at constant pressure, so I'm going to plug in the P here, and the next thing that I'm going to do is, again, I just have to write dt, because I'm dividing both sides by dt, so that will again give me curly E divided by curly T, and that is V. And again, when I divide this by dt, this dt will cut down with dt, and I'm going to be left with this part only. And so now I'm going to plug in this value in this part of the equation. We have just derived the relationship between Cp minus Cv is equal to that, and I have just explained how delta E over delta T is equal to this part, and now I'm going to plug in this part here. Okay, so now plugging in this part here will give me, okay, so now I just have written both of these equations in the back side of my page, and as you know that we have derived the value for Cp minus Cv, and we have derived the value for delta E divided by delta T. So I have just written both of these equations here, because now I am going to plug in the value for this part here. Okay, so when I'm going to plug in the value here, as you can see on your screen, that Cp minus Cv will become, and in this place I'm going to write this part, and that will give me curly E divided by curly V temperature, and curly V divided by curly T pressure, and again plus curly E divided by curly T volume, and then again this part P curly V divided by curly T pressure, and again the last part of the equation. Okay, so now what I've just done, I've just plugged in the values, and now as you can see here that this part of the equation and this part of the equation will cut down, okay, because these both are the same, and then what I'll be left with is this part only, curly E divided by curly V temperature, and curly V divided by curly T pressure, plus P into curly V divided by curly T pressure. Okay, so now as you can see that this part and this part is the same, so I can take it as common. Okay, so taking this part common will give me curly V divided by curly T into pressure, and since this part has been gone out as common, and I'm left with this part here only, and that is temperature, and then plus, and this part has gone out, I'm only left with the pressure here. Okay, Okay, so this is the change in volume with respect to change in temperature, and this is the change in energy with respect to change in volume. Since we are talking about the ideal situation here, the ideal gases here, and as you know that there are no forces of attraction or the forces of repulsion between the molecules of the ideal gas, so in that case I can take delta E divided by delta V to be equal to 0, because in the case of the ideal gases, the change in energy with respect to the change in volume is equal to 0, because we are not taking any interactions between the gas molecules. So that's why I can say that the change in energy with respect to change in volume in case of the ideal gas is equal to 0. So when we take this part to be equal to 0, what I am left with is only P, and P being multiplied by this will give me P into del V divided by del T at constant pressure. And again, as you know that PV is equal to RT, the general gas equation is PV is equal to RT. And again, if I divide this temperature here, that will give me PV divided by T is equal to R. Okay, so when I'm taking the change in volume with respect to change in temperature at constant pressure, and that means that this will be equal to R. So I can say that here this quantity can be taken equal to R from the general gas equation. So that was Cp minus Cv, and now I have taken it to be equal to R, and that will give me the final equation Cp minus Cv is equal to R. Okay, so that is our final relation that says Cp minus Cv is equal to R. So what can you interpret from this equation is that the specific heat at constant pressure is always greater than the specific heat at constant volume by an amount that is equal to R, and that is the general gas constant. So I can say that Cp is always greater than Cv.